And ultimately, linear thing is exactly the simplest thing we will study. And of course, as I said previously, the simplest thing to recognize would be the algebraically linear object. So what would be a linear function? Well, because, well, look, by the way, we consider now a function on a plane. So let me pause with linear curves. What is it that we look at right here? This is a function of two variables. And we make the value of that function change and look at the curves determined by those equations f of x, y equals some number. What about this? Is this about any function? Well, it is about some function, right? What kind of function is here? I look at this kind of condition, right? Is this somehow a function? If it is, it must be a function of p. Because a and b are fixed, those cannot be variables. So how to even think about this as a function of p, this left-hand side? What does it mean to be a function of p? Well, it means if you take any p on a plane, and if you want to have a function, that means you have to know how to associate a number, f of p, to that point. Is there any way suggested by this expression to get a number? We just literally compute that expression, right? So you take a point on a plane, you find the distance, compute it, compute that distance, add those together, subtract 7, that's your number. So the value of the number assigned to this point P is equal to this distance from P to A plus distance from P to B minus 7. That's the formula. It's not as algebraic as that formula is. It doesn't contain those x and y variables yet. But it's a formula. It's a way to assign a number to any point. So abstractly speaking, this function in this particular example is a function from a plane to a line. It takes any point on this plane and assigns a number using that formula. And now, of course, if you think for a second, there is a way to translate this description into that description. Right? How do you translate that into a function of two variables?
Use the x and y coordinates for A, B.
Choose coordinates, of course. Well, any way you choose coordinates, even with this strange coordinate system, you call this x, you call this y, right? Every point on a plane gets some coordinates, and if you assign this unknown point P coordinates x and y, then this expression becomes an explicit formula on x and y. So translation from this to algebra is very easy. What about physics? Well, the simplest example is right here, temperature or altitude. The temperature of points on that plane is a function. Right? It takes a point on a plane and assigns the number, which is temperature, at that point. Right? It might not have a formula for you, but at least you can compute that number using experiments. You can measure temperature here and there. And, well, you may want to figure out a formula just to simplify your computations, but that's a different matter. Altitude of points on a map, on a plane, right? It's also a function in some sense. you take a point on a map, and there is already a number assigned. It's altitude of that point P. So you have a function. And of course, all the advantages of algebra, that computability, comes only when you can translate these situations into algebraic language. And the straightforward way of doing that is to introduce a coordinate system, right? Take a plane, introduce the system you want, call x and y those independent variables, and boom, you have a function. And once you translated that into algebra, well, then you can work with formula, you can simplify, you can classify, you can do a lot of things that you cannot even think about here. It's hard even to think about, well, what would be the degree of this curve? Right? What's the degree of hyperbola? Or what's the degree of ellipse? Unless you already did this translation and figured out its degree too.